Hello, everyone. In this video, my goal is to finish presenting how to do the examples that we started in class on Thursday from section 6.3, adding and subtracting rational expressions. Those of you who are in class have the paper copy of the handout. The rest of you can find it as a file in the modules in Canvas. So again, this is section 6.3. Adding and subtracting rational expressions. We're working through the examples. And for the purposes of conserving time, I skipped example B yesterday. We'll do that again now, or not again. We have the algebraic fraction 2x plus 1 over x squared plus another algebraic fraction 3 minus x squared over x cubed. As with numerical fractions, when we add algebraic fractions, we need to find a least common denominator. That is the least common multiple of the denominators that we see. Here we see x squared and x cubed. I hope it's clear that the least common denominator here is x cubed itself, since x cubed is already a multiple of x squared. We must now raise the original fractions to higher terms so that we have new equivalent fractions with the common denominator. So we look at this denominator, we compare it to the LCD, and we ask ourselves, what's new? Well, what factor do we need to get from x squared to x cubed? I hope it's clear that we need to do is multiply by x. Of course, we have to multiply both numerator and denominator by x to make an equivalent fraction. The second fraction already has the LCD as its denominator, so you either can multiply by nothing at all or by the number 1. Multiplying through in the first fraction, we get distributing the x, we get 2x squared plus x over x cubed, plus the second fraction remains the same, 3 minus x squared over x cubed. Now that we have the common denominator, we write the sum as a single fraction over the least common denominator, x cubed. And as I said in class, I strongly recommend that you get in the habit of using parentheses when you add the numerators. Now, in this particular case, they don't do anything because we're adding, but if we were subtracting, the parentheses would be necessary. Since we don't need them, I will simply rewrite the fraction without them. 2x squared plus x plus 3 minus x squared over x cubed. We see now that we have like terms to combine in the numerator, the 2x squared minus the x squared, and that will yield x squared plus x plus 3 over x cubed, and that's the sum. We did example C in class, so I will go on to example D. Y squared plus z over xy cubed z minus x squared plus z over x cubed yz. We are subtracting fractions. They're algebraic fractions, but fractions nonetheless. Therefore, we seek a least common denominator. In this case, the LCD, in order to cover both of these denominators, we need x to the third power. In order to cover both denominators, we need y to the third power. We need only a single factor of z. And now this is a multiple of both of these denominators, and it is the smallest such expression that is a multiple of both denominators. So it is the least common denominator. We now take the original fractions, y squared plus z over xy cubed z minus x squared plus z over x cubed yz. And we have to ask ourselves, when we compare the original denominator to the least common denominator, what's new? What factors do we need to get from here to here? To get from x to x cubed, we need x squared. Y cubed to y cubed, we don't need anything. Z to z, we don't need anything. We just need an x squared, which I could write better, x squared. Of course, we have to multiply the numerator by that as well. Similarly, comparing this denominator to the LCD, we see that we need a factor of y squared. We multiply both numerator and denominator by y squared. Multiply this out, and we get, writing these in alphabetical order, x squared y squared plus x squared z over x cubed y cubed z minus, multiply out, x squared y squared plus y squared z over x cubed y cubed z. We now have our difference written as fractions with a common denominator. We may write the whole thing as a single fraction with that common denominator, x cubed y cubed z. The numerator is x squared y squared plus x squared z minus x squared y squared plus y squared z. And notice the parentheses this time are crucial, because this numerator, I can't just get rid of them. The first set of parentheses you can just ignore, x squared y squared plus x squared z. Well, we have to distribute this minus sign, minus x squared y squared minus y squared z, and that's over the common denominator x cubed y cubed z. Next, we simplify the numerator. Notice that we have the x squared y squared terms cancel, leaving x squared z minus y squared z over x cubed y cubed z. And at this point, you're going to feel a tremendous sense of satisfaction. You've found the least common denominator, you simplified the numerator, you're going to want to put that in a box and say it's your final answer. But remember, we are always open to the possibility that this can reduce even further. And in order to see whether it does, we have to write it in factored form. Using our Chapter 5 skills, you see that we can take a z out of the numerator, whereupon we have a difference of squares. I'll go directly to x plus y, x minus y times z over x cubed y cubed z. And boom, we see that the z's cancel, leaving factors of 1. Now, when we do that, we're operating on the assumption that z is not 0. So finally, you can multiply it out, or you can leave it in factored form. I am not picky about that. I'll multiply it back out. X squared minus y squared over x cubed y cubed. And now this one's interesting because you'll notice all the z's are gone. The final answer doesn't have a z in it, which means this is equivalent to the original no matter what x and y are, but z cannot be 0, because if it were 0, we'd be dividing by 0 in the original expression. We are always faithful to the original expression. Let us now do example E. Is the fraction 3x squared over 2x plus 1 plus the fraction 6x squared over 4x squared minus 1. Again, since we're adding fractions, we look for a least common denominator. And you might think, all right, we have two denominators. If we multiply them together, we get a common denominator. Well, it's true, but that isn't necessarily the least common denominator. Recall from class that in order to ensure that we use the least common denominator, we have to factor these denominators. This one, we can't factor any further. This denominator, though, is 2x plus 1 times 2x minus 1. So we see the 2x plus 1 is already represented there. So this is, in fact, the least common denominator. 2x plus 1 times 2x minus 1. And here we go. Our next task is to raise these fractions to higher terms so that the new denominators are the least common denominator. For the first fraction, we compare the original denominator to the LCD, and we ask ourselves, what's new? What's new is the 2x minus 1. So we multiply numerator and denominator by 2x minus 1. Conversely, this fraction does not need to change. It already has the LCD as its denominator. We may now proceed. Start by distributing here. And we get, what do we get? We get 6x cubed minus 3x squared over, I'm going to be lazy and just write LCD for now, plus 6x squared over the LCD. And now that we have the fractions over a common denominator, we may write that as a single fraction with numerator 6x cubed minus 3x squared, in parentheses for now, plus in parentheses 6x squared. Since we are adding, those parentheses are not needed. I'm feeling lazy, so I'm simply going to erase them. I could have chosen not to write them at all, but as I said, it's a good habit to do so. And now we see like terms to combine in the numerator. So simplify the numerator. And we get 6x cubed minus 3x squared plus 6x squared is 3x squared. And that's over the LCD, 2x plus 1 times 2 minus 1. However, and again, you might think you're done, but always remember it might reduce. Factor the numerator. We see that we can take a 3x squared out of the numerator, leaving, surprise, surprise, 2x plus 1. I will now write the original LCD, 2x plus 1 over 2x minus 1. And it was rigged. We see that we can cancel 2x plus 1s. When we do so, we require that it not be 0. 2x plus 1 is not 0. Simplifying this out, we get 3x squared over 2x minus 1. And then this is equivalent to saying that x is not negative 1/2. And that's our answer. Some of you might be objecting that negative 1/2 is a perfectly good number to substitute for x here. And the answer is the same. That doesn't matter. Negative 1/2 is not a good thing to plug into the original expression. That's why we have to exclude it. Last example for this section is example F. 4 over t squared minus 4t minus 3 minus t over 4 minus t. That's a t. We're subtracting fractions, so we need a least common denominator. Therefore, we must factor the denominators we have here. Our first denominator factors as t times t minus 4. And you might think that the second denominator doesn't factor at all, but remember that when the coefficient of the variable is negative, we recommend writing it with a factor of -1. We're going to write that as -1 times t minus 4. Now, this -1, if we actually keep it there, it's going to make the LCD process tedious. What I recommend you do in a case like this is take that -1 and use it to change the operation. Write this as 4 over t times t minus 4 plus 3 minus t over t minus 4. And having done that, the LCD step is easy. This denominator is already a multiple of the other one, so that's the least common denominator, t times t minus 4. We proceed as before. We take the original fractions. I didn't need to write that so wide. Plus 3 minus t over t minus 4. This first fraction already has the common denominator. You can either do nothing with it at all or multiply it by 1. The second fraction, comparing its denominator to the LCD, we ask what's new, and what's new is the t. So we must multiply numerator and denominator by t. Doing so gives us 4 over t times t minus 4, plus, distributing this, we get 3t minus t squared over t times t minus 4. Now that we have fractions with that common denominator, we can combine this into a single fraction over the LCD. Again, it's addition, so I will forego the parentheses. I know I'm breaking my own rule, but I get to do that. We get 4 plus 3t minus t squared. You might think we're done, but we're open to the possibility that this can reduce. Therefore, we're going to try to factor the numerator. I'm not good at factoring when the terms are in that order, so I'm going to rewrite that as minus t squared plus 3t plus 4 over the LCD. I'm also not good when the leading coefficient is negative, so I'm going to take a negative out of this whole thing and put it as a minus sign in front. This is minus t squared minus 3t minus 4 over the LCD. And now that numerator factors. So this is minus the fraction t plus 1 times t minus 4 over t times t minus 4. And you guessed it, it was rigged so that we have reduction here. We have a common factor of t minus 4. They cancel, subject to the stipulation that t minus 4 is not 0. And so, finally, we get the answer minus t plus 1 over t, provided t, notice this is equivalent to saying t is not 4. That's the answer for example F. All right, that concludes our presentation on section 6.3. Let us now work through the portion of the handout on section 6.4, compound fractions. From the handout, a fraction is a compound fraction if there are smaller fractions in the numerator or the denominator. If the numerator and the denominator of a compound fraction are simple fractions, as we saw in some examples earlier, we use invert and multiply. Otherwise, we multiply the numerator and denominator by one mammoth LCD that clears away all the miniature denominators. I will illustrate. Example A is 1 minus the fraction 1 over 5x, and that's all over 1 minus 1 over 25x squared. So here we have a fraction whose numerator and denominator themselves have fractions. That's what makes this a compound fraction. What we want to do is, our goal here is to get rid of these little mini denominators. So let's see. We have a 5x and a 25x squared. I hope it's clear that 25x squared is already a multiple of 5x. So that's the LCD among these two here. That's what we're going to multiply by. We multiply the entire numerator by 25x squared. We multiply the entire denominator by 25x squared. That will require distributing. In the numerator, the first multiplication, we're just multiplying by 1. We get 25x squared. Minus, now in the second multiplication, 5's cancel and x's cancel, leaving a 5 and an x, provided x is not 0. I'll write that down in a moment. In the denominator, again, we multiply. We get 25x squared minus, these cancel entirely, leaving a 1. Oh, and we canceled x's, so I need to write down that x can't be 0. Now, I'm sure that a few of you are now tempted to just cancel the 25x squareds here. Don't do that. We only ever cancel factors of the entire numerator with identical factors of the entire denominator. We do not reduce fractions in bits and pieces. Never. Just please, don't do it. What we do is we look for opportunities to reduce, and that means we have to factor. In the numerator, we have a common factor of 5x, which will leave 5x minus 1. The denominator here is a difference of two squares. This is 5x squared minus 1 squared. So we get the product of two conjugates, 5x plus 1 times 5x minus 1. And we already have x can't be 0. And now we see that we can cancel a pair of 5x minus 1s. So as a new restriction, we have 5x minus 1 cannot be 0. Multiplying this out, we get 5x over 5x plus 1. However, x cannot represent 0, nor can x represent 1/5. And if you object that 1/5 is that both of these are perfectly good numbers in this expression, my point is that they are not allowed in the original expression. Example B might give you eye strain. It's a over b minus 2 minus 3b over a all over a squared over b plus b squared over a. Again, a compound fraction. The numerator and denominator are themselves not simple fractions, so we have to follow this process. We look for a common denominator among these little denominators, the b, the a, the b, the a. Well, I hope it's clear that the LCD here is simply a times b. Not a squared times b squared. We want the least common denominator. We proceed, therefore, by multiplying both numerator and denominator by the LCD AB. As before, that requires lots of distributing. And that will yield. In the first multiplication, the b's cancel, leaving a. In the second multiplication, nothing cancels. We get minus 2ab. In the third multiplication, the a's cancel, leaving minus 3b squared. In the denominator, the first multiplication, the b's cancel, leaving a cubed, plus. In the second multiplication, the a's cancel, leaving a cubed. Since I canceled a's and b's, neither of those may equal 0. Remember now that as tempting as it is to stop here, we have to look for an opportunity to reduce. Now, it might not happen. I've rigged a lot of these so they do reduce, but it doesn't always happen. Be prepared for disappointment. I forgot a square. My apologies. A squared. I hope some of you were not sitting there shouting at me. This numerator factors. It is, let's see if I can do this mentally, a plus b times a minus 3b. Check that mentally by foiling. That works. And notice the denominator is the sum of two cubes. We have a factoring pattern for that. It's a plus b with the same operation, and then a squared, and then the opposite operation minus the product, ab. The last operation is always plus, SOAP. Same opposite, always plus, SOAP. Equal to 0. At which point we see that a plus b cancels, which means we also have a new restriction. A plus b can't be 0. And so our final answer here, this is equal to a minus 3b over a squared minus ab plus b squared. And neither a, b, nor a plus b can equal 0. In the interest of time, I want to skip to example D. Get some space. Here we have the compound fraction 1 over 2r minus 1 over 3s over 2r minus 3s. It might bother you that the numerator has miniature fractions, but the denominator doesn't. That doesn't matter. It's still a perfectly good compound fraction. If you want to imagine these as having over 1 for sort of a symmetry, go right ahead. What we need to do is to simplify this by finding the LCD of the miniature denominators. The miniature denominators are 2r and 3s. There's no overlap there at all, so we will multiply this all together to get the LCD, and that'll be 6rs. That is what we multiply the numerator and denominator by. In the numerator, I will distribute, and strangely enough, I'm going to leave the denominator in its factored form. There are no miniature denominators here to cancel, and I do want to be able to look for reduction at the end, so I might as well leave it in factored form. I'm being strategic about this. In the numerator, in the first multiplication, 2's cancel and r's cancel, leaving, well, 3s. We get 3s minus, in the second multiplication, 3's cancel and s's cancel, leaving 2r. As I said before, I leave the denominator in factored form because I want to look for opportunities to reduce. Now, you might look at this and say, well, there are no factors. The numerator doesn't factor. The denominator is already factored. There's nothing in common. It doesn't reduce. You have to look a little more closely. You'll notice, remember the opposite binomials? 3s minus 2r is exactly the opposite of 2r minus 3s. You can, if one way to look at this is to factor out a -1, factor out a -1, and that'll give us minus 3s plus 2r, which we can write in alphabetical order as 2r minus 3s. So minus 1 times 2r minus 3s over 2r minus 3s over 6rs. Again, I want to, we have opposite binomials. And so we may now cancel the 2r minus 3s. Write down that, getting ahead of myself. Let's write down that the factor that I canceled cannot equal 0. When they cancel, they leave 1s. So the final fraction is quite small. It's -1 over 6rs, or I like to keep the minus sign outside, minus the fraction 1 over 6rs. And it's okay to leave the restriction like that. It's a bit more symmetric if I move the 3s to the other side. 2r can't equal 3s. How about that? Anything in here is our final answer. Again, I emphasize you might think that this restriction does not look at all as if it's necessary, but it's necessary in the original fraction. I also know that some of you are looking and saying, what about r and s? They can't be 0 either. That's true. It is true that we can't have r and s equal to 0, but that's just it. We can still see that. Someone presented with this fraction can see that neither r nor s may equal 0. We don't have to write it down. You may. There's no penalty for that. However, there would be a penalty for not writing down this one. That's the information that we no longer see, but is crucial to the original expression having a value. That will conclude what I can do for now in section 6.4. I hope to continue again in another video. Thank you.